everyone. Thank you very much for having me here, or having me write the book, contribute to the book. I was asked to write about the spontaneous localization theories. But I mean, I must confess that that's not exactly what I'm working on. So, which in a sense, it's just extremely good, because if I can present this, that means that it can be presented by anyone. But anyway, so I'm not, so I mean, in this paper, I'm probably going to upset everyone, both the philosophers, the physicists, and the historians, because I will try to join the three of them without being neither of them. I am a physicist by training, but then I shifted to philosophy because of my interest in philosophical questions. But I'm certainly not an historian. So the history that I will talk about is just like more personal, what I know about Giancarlo Ghirardi's way of approaching his theory. This is an outline of my talk. So I will talk about, the spontaneous localization theories, what they are, starting from, as you probably expect, the problem with quantum mechanics. Mainly, the fact that there are macroscopic superposition, and the fact that there is the Collat postulate that we don't really know where it's coming from. And then this as a possible way out of this, the spontaneous localization theory. I will get into more detail about those, talking about exactly what kind of difficulties people had at the very beginning, what seemed to be necessary to address, what I called that, especially the trigger problem was bothering Giancarlo a lot, and in fact the connection with non-superluminal signaling. And then, the variety of type of spontaneous localization theory which have been proposed. I would probably not be able to cover everything in the talk. Actually, I should keep track of myself about the time, which I didn't do, which was unwise. 2:55. Okay. And then I'll talk a little bit about, something which the spontaneous localization theory has, which is very different from the other interpretation of quantum mechanics, namely that it's not empirically equivalent to quantum mechanics, so you can actually perform experiments to check whether it's empirically viable. Then I'll talk more about the ontological and explanatory satisfactory of that theory from my philosophical perspective, which has to do with the current challenges of the spontaneous localization theory program, which has to do with the connection with relativity. Okay. You all know this, but here it is again. The overall problem with the original, so I'm not going to use the orthodox, I cannot use it. So the overall, quantum mechanics, when I talk about quantum mechanics, all I mean is the one that you find in the books, namely with the unitary evolution and the Collat postulate. And we know that there is a very strong sense in which the theory is extremely, at the same time, in superposition of being empirically adequate, but at the same time kind of incompatible with the realistic reading. Right? Why do I say that? Well, in order to see this, if you don't see that already, which of course you do, the usual way of putting this is talk about the measurement problem of the Schrödinger cat problem. So you can just talk in terms of you can express this problem in terms of this trilemma and say, look, if the wave function provides a complete description of the system and it evolves according to the Schrödinger equation, then there are superpositions, right, at all scales, right? But of course, right, such superposition scales like it can't be a superposition of being dead alive are never observed. So there is a sense in which we stick with unitary quantum dynamics. The theory is, in a sense, not corresponding to our observation. So of course, right, there is an immediate way out, which has been provided by von Neumann as, of course, right, in which you just say, look, I mean, of course we're not going to observe the observation because we have a, so of course we're not going to observe the superposition because during a measurement, another evolution kicks in. The Schrödinger equation is no longer valid. What happens is that the collapse of the wave function, the collapse rule. Okay. Of course, some people may be fine with this, but some people may not. I mean, especially from a historical perspective, there would just be complete change of attitude with what physics, how physics has been done before this. So, so there are many, questions that one can raise and say, look, I mean, you said that the collapse rule is supposed to apply when a measurement is performed. Okay, so but what do we mean, right? I mean, we need to specify what we talk about when we're talking about measurement, when you're talking about observer, something like that. I mean, after all, we want to be able to say that the measurement apparatus, what it does is just follow the same laws as the stuff which is supposed to be measuring. So is it, when we're performing measurement, aren't we performing a physical process like any other? So why is that a different rule? I mean, why not? I mean, so there are a question to be addressed. And so, I mean, people have proposed various ways, and of course here I'm just going to go very fast as an introductory piece. So in addition to, so we have the problem with the Schrödinger's cat, so there is the Sander way of going out, which is just postulate the collapse rule, that's going to be fine. Okay, but if you care more about what you mean, what you're really talking about when you talk about measurement, if you want to talk about measurement processes and physical processes, then you ask for a different kind of completion of the theory. And there, we have at least 3 possible ways of what can sometimes called a more precise solution of the problem, the Schrödinger of the problem, which one is proposed by the kind of wave theory, the DBV theory, it has been called so far, which, as the usual story goes, solves the measurement problem by adding something to the description provided by the wave function. Okay, so the trilemma was either the wave function is complete or either the wave function provides a complete description or you need to modify the evolution equation if you're leaving out the possibility of many words. So this one is a proposal in which say no, the description provided by the wave function is not complete at all. I mean, I think it's important to notice that it's not, it wasn't proposed to solve the measurement problem, right, at all. I mean, now especially in a sense, in philosophy, we kind of learn that backwards, right? So we learn the measurement problem and then we see the solution. But then historically what happened is that neither de Broglie nor Bohm were coming to their theory because they had a problem of making sense of the measurement problem, providing a solution for that. Arguably, and that's of course something that we can talk about, which I'm not going to defend in particularly here, arguably the idea behind having a theory like that has to do with the fact that we want to, they wanted to provide a kind of an explanation of the phenomena in terms of, I think at least 2 people have mentioned this already, a constructive theory in the sense of Einstein. So what I call the Lego brick picture of reality, in which tables and chairs are made of stuff at a microscopic scale, they're composed, right? And what you provide explanation of phenomena are given in terms of a what we call a dynamical adaptive picture of the world. Okay, so we're not going to talk about this. Another possibility of a precise solution has been given by the Menoir theory, in which basically we're just going to say, look, it's not a problem. So we saw that yesterday in Jeff's talk, especially, the idea of Everett was that you know, he didn't like the von Neumann rule at all. It was just like, I don't understand this at all. Just stick with unitary dynamics, and this leads us very naturally to take the superposition seriously. I mean, it does. I mean, again, it doesn't come from the measurement problem. It comes from a different kind of concern, arguably. There are other problems. I mean, I thought I could throw that out just to make Simon upset. And maybe you and Jean can fight about this, about whether it is true that Everett doesn't have a problem of probability. But yeah, and that's not a point at all. It was more of a joke. So the point is that, kind of a side note, the type of explanation that I think is going on in Everett has nothing to do with the compositionality and the reductive explanation. It's more like, and I think it came up again in a talk yesterday, it has to do with explaining the phenomena in terms of principle of constraint rather than as a dynamical. So I think it's interesting to notice because, you know, maybe the reason why certain people prefer one theory over the other has to do with the type of the explanation that they favor. Anyway, so here we are to our main problem here. So Girardi and Dever in 1986, following the work of many other people that I don't have time to mention, developed their spontaneous localization theory, also called spontaneous collapse theory, dynamic reduction, or simply GRW theory from Girardi and Dever. And sometimes you say, oh, Girardi and Dever, term? Okay, I don't know. That's not a problem for me now. So the point was that, you know, they started, they wanted to, the theory was specifically designed to basically integrate the collapse rule into the dynamics. And of course, you know, the point was that, you know, you solve the measurement problem, you don't have macroscopic superposition exactly because of that. You have this stochastic nonlinear dynamic that is supposed to be taking care of the superposition. All right, so here are a couple of things that I'm going to go kind of fast through because, yes. So it was an important thing during the development of this theory that originally started out as a theory in which there was about the density matrix, about mistake. So they said, no, we really want to solve the problem as a matter of principle, so we need to have an equation for the wave function. And so, and indeed that's what happened, even if originally they didn't have that. They had the problem of, the previous models had other features, but Girardi was explicitly adamant in wanting the collapse to be on what's called the position basis, because he thought that, you know, in a kind of Cartesian way maybe, the fundamental property of matter was to have been located somewhere. And so if you need to have a collapse, you have to collapse in space. So if you need to suppress superposition, you need to suppress spatial superpositions. And so there was this trigger problem, and it's kind of funny to me, but it was just like, so one of the main idea behind the spontaneous localization theory is that you need to suppress superpositions, but not all superpositions, right? Because you want to have superposition, I mean, the cat, the dog, sorry, I couldn't help it. It's not in superposition, so macroscopic objects are not in superpositions, but, you know, we see superpositions of, arguably, we infer the existence of superposition of microscopic objects all the time, so there has to be something going on, some kind of in the dynamics, in the equation that is triggering, right, the collapse, depending, hopefully, on the size, right? That was the idea, right? The idea was that the bigger the object, right, the easier, the faster the collapse is going to happen. All right, so the fourth constraint, the fourth you know, ingredient in building up the final model had to do with certain theorems that were proposed. So I mean, of course, the original. So you may wonder, right? At least I did wonder when I learned about GRW. It is stochastic and nonlinear, right? So why both of them? It has to do with the fact that there are this theorem that they said, okay, you can't really do that. You it's really, it can't really happen that a deterministic theory can do the job, right? This the proponent of this, Girardi, Grassi, Luczynski, and also Gisant, they were doing something like that, right? So you really need something nonlinear and stochastic, right? Which leads to interesting. I mean, this is I need to say this. Interesting situation for other types of approach, like the Brody's double solution program, right? Which is a program in which you do have a deterministic nonlinear dynamics. I mean, but I don't know how. I mean, I need to study that approach more to understand how it gets around this kind of problem. But I mean, the idea of suppressing the superposition one way or another with a non-linear dynamic was around there for a really long time. Binder also proposed about decays and stuff like that, but only with stochastic theory we seem to have a more definite model. All right, so yes, so the theory, I mean, historically, and this is just like, more anecdotal histories than, an accurate presentation of what actually was going on, is that in the 60s, starting the 60s to the 80s, they were the first attempt of trying to make sense of formalizing what happened during a measurement and try to put it inside of the Schrödinger evolution, right? And the idea originally was that to treat the collapse and the equation is a phenomenological description, right? Not a fundamental theory of reality, just like an effective theory that this is what's happening at a particular level. And some work done by some people in Italy, which maybe I can talk to you later about the work of Lanza, Prosperi, and Marchelli. Yeah, you probably know much more than I do because you've studied history and foundations of business philosophy in Italy more than I did. But I mean, it was interesting that the kind of community started to work on these programs at that time. And then Girardi, Rimini, and Fonda, they studied quantum system like atom decay, right? And they tried to reconcile what's going on with quantum mechanics. But these were more like phenomenological collapse. They were really thinking that they were providing a fundamental theory of reality, and only later, Gisant, Josi, and Pearl, and some others, they were trying to propose fundamental dynamics, which had trouble with the trigger problem and with superluminal signaling. So they were not really satisfactory. So the first successful model that was developed and satisfying 1, 2, and 3, right, having an equation for pure state, no superluminal signaling, trigger problem, and position preferred basis, 4. Was proposed by Girardi and Weber in 1996. They call it quantum mechanics with spontaneous mechanization, which is kind of a mouthful. In which collapse is a fundamental part of the equation, and in which position is privileged. And initially, if you actually looked at a 1986 paper, you'll see it's a equation for rho, but actually, with the help of Bell, it was transformed into an equation for psi. So yeah, very quickly, what happens is that this is in the words of Girardi. So every physical system undergoes random spontaneous localization problems that Girardi and Weber called hittings. The nature of the hittings, right, why they occur was just left unspecified, okay, and the hitting actually act as position measurements, namely they collapse the wave function in the region D, which is called the localization accuracy, which is a measure of how spread out the wave function is. It's mathematically implemented by multiplication with the Gaussian function with that particular width, and the collapse. So the wave function is going to collapse at a particular point with a given probability, the probability given by the square norm of the localized wave function, and it has a random localization time, which is distributed according to the Poisson distribution. Right, and in between these two, the hittings, right, there is a regular Schrödinger evolution. All right. Right, yeah, so I mean, these are the sad basically. So what's going on is that you have an equation for the quantum state. The preferred basis, right, is a position basis. So the measurement position are taken to be fundamental for the reasons that I've been anticipating. The trigger problem, namely when does the collapse occur, is solved because the probability of having a localization process increases dramatically while you increase the number of particles, right? Which, I mean, there are no particles here, so you should understand more degrees of freedom. So that, I mean, if just like if you separate the wave function of the whole system into the wave function of the subsystems, right? The bigger this is, so if one collapses, everything is going to collapse in accordance. So I mean, there are two fundamental new constant of nature which has been selected appropriately so that microscopic objects they don't have, I mean, they have not very great probability of localizing, but macroscopic objects do. Okay, so it was chosen in order to make the theory empirically adequate. So interestingly, and this is in contrast with all the other, I won't call them interpretation, I will call them theories. I mean, in particular in this case, a completely different theory, more so than ever, because it makes different predictions, right? This is due to the fact that, you have the non-Hamiltonian evolution, right? So energy is not conserved, right? So some people may jump off the bus immediately and just say, energy is not conserved, what are you talking about? Yeah, but I mean, of course, the parameters are chosen in such a way that you don't see that. So there is a sense in which you can argue and say, look, I mean, why do we care about energy conservation? After all, in Newtonian mechanics, there was a theorem of, I mean, it was a theorem starting from Newtonian mechanics. Why should we expect to have a conservation of energy in a different theory? So it's not, the fact that, there is no energy conservation can be defended. It shouldn't be regarded as necessarily as a knocked out argument against this theory. It's counterintuitive, it's something that is not, maybe you don't want for other reasons, but, it's not crazy. Right. Okay. So, I mean, you may have noticed that, while I was proposing, I'm describing the theory very quickly, 5 minutes? Had to do with the fact that, the collapse is implemented by multiplication with the Gaussian. It's just like kind of I mean, this is very artificial, so people started to develop what they're called the continuous collapse theories, in which you can have a diffusion equation instead, so there are better models, which can be, yeah, all right. So, I mean, an interesting part of this has to do, and you can find it in the paper, which of course you know already because of the talks that were before me. There is an interesting idea that has to do with the fact that, the collapse may be connected with gravity, which has been developed for different reasons by Yossi and Penrose. Penrose was motivated arguably by the fact that there is a tension between collapse and the principle of general covariance, and Yossi instead didn't really like the parameters, right? The parameters looked very artificial to him, so he's trying to get away, try to pair, understand the collapse in terms of gravity with the, okay, he actually couldn't really do that, but he could reduce that to 1 parameters. So here is just like a very, pictorial presentation of the testing that is going on for the theory. So, I mean, when it was proposed in 1986, I mean, we didn't have enough technology to try and test this, but you can imagine, especially, you know, in the cases in which you have energy increase, right? You can test this stuff when in super cold things like the experiments in super cold atoms, or you can just check the sound emission due to the energy increase, or you can even mention and try and measure in the loss of coherence of certain systems. And so they're going and there's, you know, restricting more and more the space of possibility of GRW, of the empirical viability of GRW, which there is a sense in which this is kind of disappointing for the proponent of the GRW person, because you know, you would expect the definer, I mean, as John was reminding me yesterday, you know, you keep doing experiment and you keep, you know, between quantum theory and GRW, and quantum theory always wins, you know. Now the space is going smaller. Yeah, all right. Okay, so yeah, all right. So this is a very long thing that, yeah. So I mean, people have let me, okay. Right. Okay, let me just talk about this very quickly. So what happened is that Girardi. So here's something that you may want to say. So if you have the wave function, I don't remember who said it, but someone did. They were talking about how de Broglie was unsatisfied with the wave function being in configuration space. I mean, Girardi has a very similar concern. And so he said, okay, I have this theory, it's about the wave function, but the wave function is not the right kind of thing that describes tables and chairs, so let's try and add some additional ontology, and he proposed a matter density field on top. Okay, and so you can actually, yeah, you can have different, I mean, it's going to be interesting because you can also talk about the possibility of testing the theory in terms of the ontology. You can say, okay, right, so if it's a theory of particles, then there's not going to be any constraint, but maybe if it's a theory of mass density, forget about the last one which I didn't talk about, it may, I mean, in certain cases, the ontology, because in that case, you're not looking at the wave function, you look instead at the mass density, then the situation would look you would need to provide certain constraint about what type of mass density would give you back the right predictions, and that would restrict the space of possibilities as well. Yeah, so I wanted to make a remark about you know, the connection of relativity. So I mean, the reason why I got very interested in, and then I'm going to stop. I got very excited about the GRW theory for a while because it seemed like it is in a sense, right, potentially more compatible with relativity than other theories. Something that already Wayne talked about before, that it seems to have. So there are different ways of talking about you know, a theory compatible with relativity. You can talk about Lorentz invariance. You can also talk about instead preservation of this the Minkowski spatial temporal structure. And it seems like for the spontaneous localization theories seem to be having less trouble preserving the second than the alternatives. But of course, this is just like you know, new research that people need to get going with, and so I think that Giancarlo would be very happy about this conference, and I hope he would be happy about me presenting this theory for him. Anyway, thank you very much. Let me have you. Yes. Okay.
Go immediately to the coffee break.
Question.
Okay. Is there
Oh, okay.
Yeah, I've always wondered what do proponents of collapse models have to say with respect to decoherence, because I find it a bit inelegant and even suspicious that we have two different phenomena that destroys very, very quickly superpositions.
So, yeah, so
So it's very strange because decoherence solves the problem of disappearance of superposition in macroscopic objects, but collapse models adds another very, very strong phenomena that does the same.
Right, so so is your claim that the coherence is, I mean, we don't need this kind of theories because the coherence is enough in regular quantum mechanics? Okay, so I would have to disagree with that completely, because I mean, if you get to the universal level, there is no observer collapsing anything.
Yeah,
so.
we need this to solve the measurement problem,
Yeah.
but this solves the measurement problems, but also adds a very strong phenomena destroying superposition, whereas decoherence already did that. Do you see what I mean or not?
Yeah, I mean, as far as I see what you mean, I think that the coherence alone cannot help.
Not for the measurement problem, but for the disappearance of superposition, yes, decoherence solves that.
That's not, I mean, okay, so if you think of a theory in which you're just talking about the phenomena, you may be happy and say, look, I mean, the interaction with the environment is going to collapse everything that you need to collapse, but then you need to go, I mean, no? I'm missing your point.
The rest of won't reason it.
Yeah, I don't think so at all.
So, we'll wait with okay, two information.
Someone will read the book and
Spontaneous correct, but his answer was correct.